So we are the Open Air Noise Reduction Group. In our group, we have Philip, Taylor, Jason, Zachary, and Alex. And our advisor for this project was Dr. Pai Wang. So with this project, our main goal was to look into how we can reduce noise around traffic transportation, so either highways or, as this picture says, train. And we have found that most of these noises are centered around 1,000 hertz. And the main way that we've wanted to do this is through a Helmholtz resonator. So a Helmholtz resonator is basically a cavern that is left open on one side. And when sound goes over this cavern, inside it causes the air to vibrate, which will dissipate the energy in the cavern. And basically, the frequency of this reduction really depends on the shape and size of this resonator. So our main goals is to actually create a 2D abacus model of these resonators to determine the size, number, spacing, and location of sound reduction to kind of get a good idea of what we can do with these resonators. We then want to build using our best optimal results and test it in a real-world environment.
We tested these several different models in a modeling software called Abacus. It's commonly used among engineers to simulate real-world environments. And especially for us, it was to simulate sound. We created several 2D models to help us decide the spacing, number of resonators, and location and shape, like we talked about in our goals. Some important aspects to note on our model, as you can see down here, there's a good picture of one of our models in action. The right boundary is where the sound source is. It's simulating a sound wave, so it'll be a sinusoidal wave with a positive and negative pressure, which you can see with a blue and red wave. The top and the left boundary are actually non-reflective boundaries that simulate open air environments. And the bottom boundary is a reflective boundary to simulate the ground. As the sound wave propagates from the right boundary to the left boundary, you can see it oscillating up and down like a sine wave would. And then you'll see a pocket of green color towards the resonators on the bottom left, which is the resonators actually reducing the sound pressure to a level of 0, which is about what the green color is. From our several testings, we figure out the optimal size for each resonator and shape, which is a rectangular volume. The specific sizing can be seen on the slide right here for each resonator. We figure the best number of resonators is 4, and the spacing between them is 0.17 meters or 17 centimeters. And then the best data location would be the left boundary up a little bit at 16 centimeters up, or 34 centimeters from the last resonator.
So once we found the optimal sizes of the resonators as well as the spacing, we decided to 3D print these sizes. And we used a plywood board as the flat surface that we would be testing on. This can be seen in figure 4, and then figure 5 has the speaker on the left boundary that will simulate 1,000 hertz signal across the plywood we have 3 iPhones collecting sound at the same time at different locations as found from the Abacus model as well. On the table here, you can see that the Abacus model had a positive reduction for every location, where in the real life, we had a positive reduction at right behind the last resonator, but a increase in sound actually at the 2 other locations. From this conclusion, we found that these resonators will work. The location will definitely have an influence on the sound reduction, but in the right spots, it will create a noise reduction. We also found that we were not really using the proper sound equipment, and we think if this was tested in an ideal environment, it could reduce or produce positive results.
This clip is the contour plot created in our abacus analysis with acoustic pressure waves traveling across the resonator plane. The acoustic pressure load we added to the system is a line source rather than a point source, with the bottom plane as a solid boundary and the top plane and side planes are both simulated as an open air environment to create simulated infinite space. In our analysis, 3D modeling was unnecessary as it would add a lot of variables that are not needed for sound modeling.
Since you've already seen the theoretical part of our project, I'd like to show you the experimental part. So right here on the left, we are using a tall speaker to create a line source of 0.5 meters. Across, we have the control volume of air that we'll be testing on. This is just a flat plywood board. The resonators will be placed in next to take care of the actual experiment. And then we have placements of the sound equipment, which is just iPhones. In this case, I only have one to show you, but we used an iPhone in different ways. Here, which would be right where the edge of one of the resonators would be. Back here, which is 34 centimeters across. And up here, which is 34 centimeters and across and 16 centimeters up. This was determined to be, based on our theoretical calculations, the best place. So let me show you the experiment. Okay, now I have replaced the control volume with the experimental resonators. As you can see, there are 4 resonators, which are put underneath the board. These resonators will be directly compared to the ones that we create in Abacus for theoretical testing. Once again, we have our 0.5 meter line source here, and then we have the 3 places, 34 centimeters, 16 up, 34 centimeters, and then right in front of the last resonator. Although this does accurately portray our Abacus theoretical setup, we were not able to get very good data, which we assume to be from our sound testing equipment and our environment. Although our professor did recommend us to use this kind of environment and sound equipment, it was not accurate enough for us to get data that we could actually form a true conclusion off of.